Okay, so let's get started. First of all, let's start to review what we learned last week. Last week we learned the interrupts, and you know that the interrupt is pretty close to the jump or call instructions, in the way that while you are running the main program, suddenly you are jumping to another program and call the service routine. In this case, it's a subroutine, or in this case of an interrupt, it's called the interrupt service routine. So suddenly, you're jumping to other program, subroutine or service routine, and you come back. After you're executing the service routine, you come back to the main program and continue. Okay? So some way, it's similar to the jump. However, the difference of the interrupts is that there's no instruction for jumping. So there's nothing like a jump or call instruction. There's nothing. Suddenly, whenever something happens, whenever some interrupt event happens, then you jump to interrupt service routine and execute whatever you have in the service routine and come back. After you executing all that, you come back where you left off. Okay? So that's the interrupt. So in the main program, you don't see anything. Suddenly you jump whenever the interrupt event happens. We have 5 different interrupt sources in 8051, 2 different timers, 2 different external interrupts, and serial port. Remember the condition of the interrupt, right? We learned that there are 3 different things, and in order for the interrupt to occur, we have to have 3 different conditions. We have to have 3 different conditions. The first one is that actually the interrupt event should occur. For example, right, in the example of your home, let's say you're at home, you're reading a book, and your friend is calling you. In that case, interrupt event is same as like your friend, and your friend is calling you. Okay? Only when your friend is calling you, your phone rings. Otherwise, your phone does not ring. So this event means that actual event, like your friend is calling you or someone is knocking, that's kind of event. So your actual event should occur. And second condition is that interrupt flag for the event is enabled, which means that your telephone has to be plugged in your home, right? So your telephone is activated, or your doorbell should be enabled. Only then someone is calling you, then your telephone rings. Okay, if the telephone is not there, then someone is calling you, there's no telephone, so there's no ringing. Okay, so in order for the telephone to ring, you need to enable the telephone. Additionally, the last condition is that all of the interrupts are enabled. This one is same as like electricity in your home. Okay, you need to have electricity so that your telephone is enabled. Your telephone should be plugged in into the wall outlet, so that your telephone is now enabled. Even though you buy a telephone, if telephone does not have electricity, the telephone does not work, right? So you need to have 3 different conditions to meet. The first one is all of the interrupt, or we can say global interrupt. Global interrupt is enabled, and out of these many interrupts, we have 5 different sources. So actual interrupt, like for example, if you want to have a timer 0 interrupt, then you need to enable timer 0 interrupt. Okay? For each interrupt, you need to enable it. This is the enable for all the interrupts, and this is the enable for each interrupt, and this is the actual event. Okay? So we need to have these 3 conditions. Only then, this is the end, right? All these 3 conditions has to be there. It should be 1, 1, 1. Only then interrupt will occur. When interrupt happens, these are the operations that there's going to be done. First, your current program counter will be pushed to the stack. Why do we do this? Actually, hardware do this. We don't have to do this, but we need to understand what happened in the hardware. So hardware, the microprocessor will push the program counter value onto the stack. That's the first thing to do. Why do we do this? Because we need to come back later on. Okay? Once the interrupt happens, then you need to jump to the interrupt service routine, do whatever you want, and you need to come back, right? So in order to come back later, we need this program counter, the current program counter. So you need to save this one into stack. Okay? And since this interrupt can happen anytime, okay, unexpectedly, this can happen anytime, what you need to do is that you need to have a program interrupt vector. Interrupt vector is the destination of your jump. Whenever an interrupt happens, then you need to jump. You're going to jump to interrupt vector, right? So you need to prepare the vector. That's another thing. And inside the interrupt service routine, at the end of the service routine, you have return I. I means interrupt. So whenever the return I instruction is executed, now the program counter will be restored from the stack, and it's time to come back to the main program. Okay, so these are what's happening. And remember that since we have 5 different interrupts, if you need, it depends on you. You're going to set this priority. Okay, so it's up to you. So if you want, when you enable multiple interrupts, if you enable only one interrupt, then there's no use of priority, since there's only one, right? You don't have to do it. But if you want to enable 2 or more interrupts, then you want to set the priority, okay? Because you need to think about which interrupt is more important. Okay, more important one, you want to set it as a higher priority. Because sometimes, right, each interrupt is independent. Okay, the example that I show you is something like this, right? We have a telephone interrupt, we have a doorbell interrupt, and sometimes, right, when you're reading book, telephone rings, and at the same time, someone is knocking. Both one at the same time, right? Both events may happen at the same time. In that case, which one do you want to receive first? That's a priority. Or maybe, let's say, telephone rings first, so I go there and pick up the phone, and you talk to your friends. Okay? While you're talking to your friend, someone is knocking the door. In that case, if you think that this is a high priority, then you're going to ignore it, because this is important for me. But if you think that someone is knocking the door, so that is more important, if that is a higher priority, then what you're going to do is you can say, oh, hold on, don't hang up, hold on, and then go there and check who he is, okay? And then come back and keep talking, right? So depending on which one you want to set it as a higher priority, the operation is different. So that's why if you want to enable multiple interrupts, you want to set the priority. These are the registers that you want to set in order to enable the interrupt. We have an enable interrupt, interrupt enable register. Looks like this, right? So this, the first bit, MSB, most significant bit, is global interrupt. So interrupt enable. So this one is for enabling all the interrupts. And the rest of the 5 bits here, the last 5 bits, these are the interrupt enable for each interrupt. So this is, for example, the last bit. LSB is to enable the external interrupt 0. And that's the timer 0. Okay, so if you want to enable, let's say, I want to enable timer 0 and external interrupt 0, then you want to set these two, 1, 1. And the other 3 bits, if you don't want to use it, 0, 0, 0. Okay, then you disable it. And also, since you want to use the interrupts, of course this one has to be 1. If you make this 0, then all these things will be ignored, right? So you need to make sure that this will be 1 and 1, 1 if you want to use 2 interrupts. And in this case, if you use 2 different interrupts, now you need to think about which one is a higher priority for you. So as an example, let's say, oh, I think this one is more important for me. In that case, in this priority register, you want to set this one. This one is the priority external 0, right? This one corresponds to this one. So you want to set this one as 1, because I think in my case, external interrupt is higher priority than timer. So you want to set this one to 1 and the primary priority you want to make it 0. Okay, depending on what you want. In order to use the interrupt, you need to have an interrupt vector. And what was the interrupt vector? This is the known location, known destination when you do jump. Again, interrupt happens unexpectedly. Okay? Let's say in your home, right? You're reading a home, but your friend is calling you. But the telephone rings at any time and random time. You never know when the telephone rings. Same thing here. You are reading a book, you are executing your main program, but suddenly interrupt happens. Right? And no one tells me where to jump. So this is where to jump. Whenever interrupt happens, you are going to jump to this one. And depending on which interrupt you get, let's say you are getting the external interrupt 0. Okay? In that case, if this event occurs, then you're going to jump to this location. This is where to jump. If the timer 0 interrupt happens, then you're going to jump to this address. So this is the destination address whenever you have an interrupt. Okay? You're going to jump to one of these. That's called the interrupt vector. Okay? You're going to jump to one of these. This is an example, right? So here, what is a 0013? Let's go back here. 13 is reserved. This address is reserved as the interrupt vector for external interrupt 1. So whenever the external interrupt 1 happens, then I'm going to jump to this address. So as an example, let's see. This is where you jump, right? So here's your main program. As you can see in the assembly here, my program starts from here, and I place my program into the address 100H. So this is where my program is. And every time you reset the microprocessor, like a reset, then you always start from here, right? This is the base address. So you always start from base address. But in my base address, I have an instruction called the long jump start. And where is the start? This is the start. So therefore, when you reset it, so this is called the reset vector. Okay? All these things are vector, but this is called the reset vector because when you reset it, you jump to here. It's not a jumping really, it's you start from here. So this is why we call this one as a reset vector. When you reset it, you start from here, and this one actually is a long jump to start, so suddenly you jump to here. And this is where your program is, and you are executing your program. Like this, right? So while you are executing your program, suddenly, unexpectedly, you get an external interrupt 1 at this time, at some random time. Once that happens, then based on this interrupt vector, we are going to this is a reserved. This is a known location of interrupt vector for external interrupt 1. So you are going to jump to there. So this is where to jump. Okay? So while you are running the program, suddenly external interrupt 1 happens. So you're going to jump to there. But here we already programmed like long jump ISR external 1. So by the way, these are not automatic. You need to write this code here. That's why I write it this way, right? So I put the original 0000. At this location, I'm going to write this instruction. At 13H address, I'm going to have this instruction. At 100H, I'm going to have my main program. At 200H, I have my ISR, interrupt service routine. Okay? That's why you need to make a program like this. Once you do this, right? Once you write the program like this and you assemble it, like using assembler, and then download it into the memory, this is what's going to happen. This is how your binary will be located in the address map. Suddenly, external interrupt happens right here. You're going to jump to interrupt vector, and inside the interrupt vector, you have a command long jump ISR external 1. And this ISR external 1 is right here, right? Right here. So therefore, you jump to there because of interrupt, and suddenly, because of this instruction, you're going to jump to there again. And this is where you execute your interrupt service routine. And you keep doing. You're executing your interrupt service routine, and at the end of the interrupt service routine, you have return I. You have a return I. You have a return I. So therefore, you're going to jump back. You're going to jump back to your main program and continues. Okay? So it looks like it's complex, sounds like, right? Because think about the call and return. What happens in the call return is that this is your main program, and whenever you have a call subroutine, then from here you jump to subroutine and executing the subroutine, and whenever you have a return, you come back to here, right? So it's a jumping to here directly and come back here. It looks like simple, but in this case, it's like coming back here and come jump to there again. Looks a little bit complicated, but we need to make it this way because interrupt happens at random time, and interrupt does not tell you where to jump. So therefore, we need to have this kind of interrupt vector. This is where to jump. When interrupt happens, this is the destination. And once you jump to this destination, now the problem is that between these, right, we don't have enough space to put your ISR. Okay, interrupt service routine, sometimes big. Whenever your interrupt happens, then you want to do a lot of things. You don't have enough space to put your interrupt service routine. Therefore, for each interrupt vector, you want to have a long jump. So therefore, your actual interrupt service routine is somewhere else, and based on the interrupt vector, whenever interrupt happens, you first jump to interrupt vector, and inside the vector, you are jumping to your own program of ISR and do whatever you want, and then come back. Okay, it's like jumping to ISR, jumping to interrupt service vector, and jumping again to your own program. Okay, that's why we need to do this in interrupt. Okay, so it is important to understand this whole procedure. And this is a little bit more complex example. Since we have 5 different interrupts, if you want to enable all these 5 interrupts, then you have all these interrupt vectors. Look at this one. 000H address, we have a reset vector, long jump start. And this is the interrupt vectors for each of the interrupt sources. Okay, each of these sources, we have an interrupt vector. We have 5 different interrupt vector, and all of them are long jump. Okay. So how to make the interrupt work? First thing is that you want to configure the registers. What do you want to do in the register? There was a interrupt enable register. Remember IE register? In order to make the interrupt work, you need to set this one to 1. Only then the interrupt will happen. And if you want to use, let's say, timer interrupt, then you want to make this one to 1 also. If you want to, have a timer 0 and external interrupt 0, want to make both to be 1. Okay. So which interrupt you want to have, depending on that, you want to make it to be 1, and this one is a global interrupt, so you want to have 1. And if you need, 1 second. If you need, then you want to set the priority. If you need multiple interrupts, then if you need, you may want to set a priority. Okay? So some of the registers has to be configured that way. In addition to that, you need to program the others. Let's say, what interrupt do we have? timer interrupt and external interrupt, for example, right? That's actually what we're gonna look at today. But let's say you want to enable the timer interrupt. Okay, in that case, again, you are gonna set the global interrupt and timer interrupt bit to be 1, but you also have to set the timer registers. Only then the timer will work. We need to have a timer hardware. That's gonna be the interrupt event. For example, right? Coming back to your telephone example, let's say I have my electricity in my home, which is global interrupt, and I have a telephone and I plugged into the wall outlet. So that's like I enable the timer interrupt. But your friend has to call you, right? That's the interrupt event. Only then the telephone rings. But let's say why your friend is calling you. Maybe he's calling you just to say hi, but generally you and your friend already talked. Okay, maybe you want to talk to homework or something. So your friend is say that, okay, I'm gonna call you tomorrow. So you kind of agreed. You make an appointment, right? Only then your friend is calling you. Same way here, in order to use a timer, you have to set the timer. That's what we're gonna talk about in a minute. We need to set a timer hardware. Okay, and this timer hardware will give you the event. Okay. So again, what I'm saying is that what we talked about so far is to enable the interrupt. But you need to have another part which enable the event. If you want to have a timer interrupt, then you need to set the event, timer event. Let's say if I want to enable the external interrupt, then you need to have the external event. What could be the external event? Let's say you have a microprocessor, and you know that later on I'm going to show you, but this is a 8051, right? This is a chip. And in the chip here, we have a external interrupt pin. Interrupt 0, interrupt 1. Remember that? These are the pin, actual pin, in order to get the external interrupt. So for those pins, what do you want to do? Maybe you can connect this pin to the keyboard. Okay? That's like an external interrupt. So whenever I click the keyboard, okay, then by the time you push click the button, it gives you interrupt to the microprocessor. Okay? So you need to connect this pin with the keyboard, and you push the keyboard. That's the event for the external interrupt. Okay? We need such kind of event. Only then the interrupt will happen. And also, in order for the interrupt, you need to prepare the interrupt vector. Okay? So those things. So let's talk about counter and timers. That's the topic today. These two are actually similar, counter and timer. Those two are pretty similar. So first of all, let's talk about why do we want to do this? Okay, why do we want this? First of all, counter is typically to count the number of external events. As a previous example, right? Let's connect the external pin into the keyboard, and you want to push the keyboard like this, right? And maybe sometimes you may want to count how many times I push the button. Okay, you just keep pushing, and inside the microprocessor, maybe you want to count how many times I push the button. Something like that. That's counting. Okay, that's counting. That's one of the reasons why we want to do this. Second reason, which is more popular reason, is that you want to make a certain delay. For example, right? Let's say in my program, I want to have a delay of 1 microsecond or 1 millisecond. Okay? We have many software that doing this, right? We need a delay many times. In that case, how do you know that's going to be 1 millisecond? You want to make a delay exactly 1 millisecond, but how do you know? Someone has to count, or someone has to measure the 1 millisecond. So microprocessor will do it for you. What you need to do is to set the timer or set the counter and enable the interrupt and let the hardware do it. The hardware will count and measure the delay and make sure that it becomes 1 millisecond. Something like this, right? That's the second reason why we want to do this. Okay, precise internal time delay. So I'll tell you a little bit more on that in the next slide. So how we can do this? We want to do these things, and how you can do this? Let's think about the delay. How do you make a delay? Let's say I want to make a delay, a certain delay. How can you do it? Generally, there are 3 different ways. The first one is easiest way, pure software technique. How can you make a delay in the software? Let's say in our assembly software, how can you make delay? Delay in this case means that you want to do nothing for a certain amount of time. That's delay. For 1 millisecond or 1 millisecond, I want to measure 1 millisecond. I don't want to do anything. In 8051, let's look at this one first. What we can do is that there is a operation or instruction called NOP. Okay? NOP is actually doing nothing, no operation. So no operation actually is operation. Okay? This one is operation, but doing nothing. Just killing time. Okay? So if you, in this particular example, what you are doing here? What we are doing is that see here that we have DJNZ. It's a conditional loop, conditional jump. And we have another DJNZ. So here it's like you have a loop, inner loop, and outside that you have another loop. It's like a double loop. So you're doing keep looping here, and inside the loop you have NOP. Okay? So basically you just keep doing NOP so many times, which means you are doing nothing for a long time. While you're doing looping, you are doing nothing because inside the loop it's NOP. So eventually, once you do all this looping, and after that, it's just delay. So this is the easiest way to make a delay. So within a certain delay, I have all NOP. Okay, in that case, you are doing nothing for a certain amount of time. Probably easy way, right? In this case, what you need to do is write the program this way, like keep looping with the NOP, and you don't need anything else. That's the software technique. What's the problem of this subroutine or program? The main problem is that in this case, it is a pure software technique. So therefore, when you are measuring the delay, you are doing nothing. Okay? Because it's NOP. So you cannot do anything else. You are basically just killing time. And this microprocessor will be idle, will be doing nothing while you are measuring the delay. That's the problem. Why is there a problem? Let's think about this way. Let's say I want to, let's see. Let's say let's say I have a TV here. Okay, I want to check my TV. I want to watch some TV program. Okay, so in that case, let's say I want to check the TV and every minute. I have something else to do. Let's say I was reading a book and I was waiting for a certain program, TV program. Okay, and while I was reading the book, I go there and turn on the TV, and if the program starts. If the program doesn't start yet, then I come back here and keep reading the book. Okay, and I'm basically waiting the TV program. I want to see the TV program, but TV program has not started. So before that, I want to watch it. I want to read the book. Okay, so how do you know when the program starts? Maybe the probably the dumb way, which is actually this way, is that forget the book and go there and watch the TV until the TV program is on. Okay? You just keep watching the TV, and at some point, maybe the TV program will start. Maybe it takes like maybe an hour, or maybe 2 hours, but at some point it'll start, right? So you just go there and watch until it starts. That's something like this. That's something like this. I don't know, is this a good example or? Okay, so what I'm saying is that you have something to do. In my example, I want to do my own work. I want to read my book. Okay? But there is something else to do, like watching the TV or something. So if you use this software programming, software technique, then you cannot do your own job because I have to do these things. Microprocessor will do these things. And these things actually is doing nothing. But in order to do these things, I cannot do my own work. Microprocessor, this is software, so microprocessor has to execute these things, right? And actually this routine is looping with the doing nothing. But from the microprocessor point of view, still this is some work to do, right? So I have to do this, microprocessor has to do this, so I cannot do my own work. That's the problem. If you want to compare these two, then I think it's probably better to understand. The better way, actually, is like a joint effort of software and hardware. So I'll tell you what this means. This one, sometimes called the software hold timer. In this case, what happened is we have a hardware. In the previous one, pure software technique, you don't need any hardware because we do everything in software. But in this case, since you are doing everything in software, you need to measure the 1 millisecond. Okay? Let's say I want to do something. I want to do something in every millisecond. Then you need to measure millisecond. You have to keep looking at the watch, and you need to measure the millisecond. That's what you're doing, right? You are basically doing loop, and you are measuring the delay in this case. But in the software hold timer, we have a hardware, like hardware timer. We are using the hardware timer. In this case, what happened is, you means the software, okay? For software, what we have to do is we are program the hardware. So you need these things. What is these things? This is like configuring the registers. These are timer registers. Okay, I'm going to tell you details in the next slide. So these are the timer registers. We are going to program these timer registers. Once you program the timer registers, now the hardware timer will run. And the hardware timer will count the millisecond. For software, for me, I don't have to count. But instead, what I need to do? I need to go there and ask the hardware, okay, is it millisecond now? The hardware says, no, not yet. Then I come back here and I keep doing my work. So in this case, software, I can do my own work. What you need to do is that maybe from time to time, I have to go to hardware and ask, okay, if the timer fires. If not, then I come back here and keep doing my own work. So we are using the hardware timer. Actual measuring, okay, actual timer runs in hardware. So software, you don't have to do anything on the timer. But the software only check the timer. Okay, only check the timer. That's why we call this polling. What is polling? Polling is like every time, like every second, I'm just checking. Okay, checking. That's a polling. So from the software perspective, software do just polling every time. And actual time measurement is done by the hardware. So that's this one. So in this case, we need hardware timer, because actual delay measurement is done by a timer. And for software, we just keep checking if the timer is done or not. That's the second way. Last one is pure hardware technique. So let's look at what that is. So the last way is a pure hardware technique. In this case, you need a hardware timer, of course. And not only that you have a timer hardware, you also enable the interrupt. In the previous two techniques, it is nothing to do with the interrupt. You don't need any interrupt. But in this case, you need hardware timer, you also need interrupt. So let's see what it is. In this case, here's how things work. I'm doing my own work, like I'm reading my book. Okay, I'm doing my own work. Before that, actually, you also have to program the hardware timer. Look at these registers, right? You are programming the register, timer registers. So once you program the timer registers, now the timer hardware will run. Okay? Now once the timer hardware run, and whenever the hardware timer becomes 1 millisecond, then now it gives the interrupt to the software. So from the software perspective, I don't have to go and check. What I need to do is that I'm going to do my own work. And whenever hardware have 1 millisecond, it gives me interrupt. Okay? So I don't have to go there and check. Because what I need to do is I just wait interrupt. Okay? Whenever interrupt comes, that's exactly 1 millisecond. Because the hardware will measure every millisecond. And every millisecond hardware will give me interrupt. Okay? Then inside the interrupt routine, service routine, you can do whatever you want. So here, let's see example. Let's say I build up let's think about this. Let's build up I have some microprocessor with LEDs, okay, like flowers with a red LED. And what I want to do is that I want to make this LED on in every 1 second, like this. Okay, let's say that's what I want to make. 1 millisecond every time, 1 second every time. How can you do it? One way to do it is that in your software, maybe you are measuring 1 second with a delay. Okay? In this case, you have to measure it, right? Because it's done all by software. So maybe you measure it. Maybe you try 1,000 NOP and measure how long it takes. Maybe it's not 1 second. In that case, you can increase the number of NOPs to 2,000 and measure it again. It's still not yet. You have to keep doing it. Okay? It's up to you. You need to measure it because it's all done by hardware. But anyway, you measure the delay, and once the delay is done, then right here on the next line, you can turn on the LED and do a loop. You can do that, right? That's probably the bad way, stupid way of doing it. Better way, little bit better way, is this one. And you program the hardware. Now then hardware timer will count 1 second. You don't have to do anything. The hardware will count 1 second. But in this case, the problem is that we don't have any interrupt. So hardware will basically measure the 1 second, but it doesn't tell the software. So that's why from the software perspective, you never know. So that's why you need to go ask every time. Okay? Is the 1 second done yet? If not, then you come back. And you have to keep checking. Hardware will measure the 1 second. Because we are using hardware timer. Okay, hardware will measure the 1 second, but software doesn't know, so software have to check. That's another one. Actually, the best way is to use this one. Okay, in this case, Software doesn't do anything. In order to flash the LED in every second, what you need to do is that you need to program the hardware timer, okay, for 1 second. In that case, the hardware will keep running and measure 1 second. And every time 1 second happens, then it gives the interrupt to the software. Then what do you need to do in software? Whenever interrupt happens, then inside the service routine, interrupt service routine, I'm gonna turn on the LED. Okay? Inside the service routine, interrupt service routine, I want to enable LED. I want to turn on the LED. Once you do that, whenever interrupt happens, then I'm gonna turn on the LED. Then it's exactly like 1 second, you see the LED is on. Okay? So that's what happened. So that's the so simply speaking, this hardware technique with the interrupt service routine, that's the best way to use the timer. So far, what we talked about is how to use the timer. Okay, how to use a timer with the interrupts. Okay, but in order to use it, right? Sometimes you may want to use 1 second, or sometimes you may want to 1 millisecond. Okay, depending on what you want, sometimes you need a different delay. So these are how to program the timer part. As I said earlier, you need to enable the interrupt part, okay? And you need to enable the hardware timer part. And this is a hardware timer part. In order to use the hardware timer, you have to program these things. Only that way the hardware timer now will run. Let's look at hardware timer registers. This one is timer control register. So we are going to control the timer based on this register. Timer mode register. Okay, we have 2 different registers. And in addition to that, we have also the other timer registers like this. Okay, so I'll tell you one by one. So first of all, let's look at briefly look at one by one. Here, the number 0 means timer 0. 1 means timer 1. Okay, we have 4 bits with the 0. The other 4 bits with 1. So these 4 will be timer 1, and these two will be, those 4 are related timer 0. Same way, here in the mode register, timer mode register, the lower 4 bits are related to timer 0, and the upper 4 bits are related to timer 1. We have a 2 timer interrupts. Right? Remember, we have 5 interrupt sources, 2 timers. So timer 0, timer 1. Okay, so it's basically the same thing. So we can only talk about 4 bits. Let's pick one timer, timer 0, let's say. In timer 0, we need to control only these 4 bits and also these 4 bits. So let's look at one by one. We need to know this one. Okay? This is probably the most important thing. This one is time. T means timer. F means overflow. Okay? This is overflow flag in timer. Right? I'll tell you what that means. Next slide. This one is a run. In order to run the timer, you want to make this 1. So this is the same as enable, right? Enable bit. You want to enable the timer, then you want to make this to be 1. Okay? This is like enable, disable. These 2 bits actually are not important, but this one are H flag, signal type control bit. Let's skip this one. Probably we have a chance to talk about details later. In the mode register, in timer mode register, we have 4 of them, and I'll tell you one by one in the next picture. So here is the hardware logic. This is actually what's implemented inside the hardware timer. Okay? The hardware timer is again hardware, so there is a logic inside. So this is a logic. We have 2 different sources for this timer. Okay, two different sources for the timer. First one is oscillator. What is oscillator? It's a crystal. It's inside the board, right? You have a clock oscillator, clock crystal. So what is the oscillator we use in 8051? Do you know how many hertz we use in your board? Generally, it depends on the board. I think your board is probably 12 megahertz or 24 megahertz, one of these. So suppose that we are using 12 megahertz. Okay, every board has a certain frequency to run. Our Intel processor, you know that it runs like 1 gigahertz, right? Something like that. So in 8051, our board, it has oscillator or clock frequency. I think that's probably 12 megahertz or something like this. So this is the clock frequency, 12 megahertz. And this one actually generates clocks. And clocks looks like this, rectangular pulse, right? So you are going to get the rectangular pulse here. And that rectangular pulse has the frequency of 12 megahertz. Now those are 12 megahertz clock, you're going to divide by 12. So therefore, here was a 12 megahertz, but 12 divided by 12. So right here, it's going to be 1 megahertz clock. Okay, right here. That is the input 1. That's the input to your timer hardware. Okay, 1 megahertz clock. Second source for this timer hardware is this one. This is the input source for the counter. You see that this is the timer, this is the counter, and we have another source for counter. And what is this source? This one says a T10 input pin. What is the T10 input pin? Look at here. We have this one right here. Okay, this is a 8051, our microprocessor, and our microprocessor has a pin T0 right here. What this basically means is that for this particular pin and 8051, you can now connect some clock right there. Okay, some clock, not this one, but external clock, whatever clock you want. From the external, you want to connect to here. So in this case, maybe you can connect like this. So now suppose that using this pin, maybe you can connect to your own hardware. Let's think about this way. Let's say you know the motor, right? Motor. Let's say I have a certain hardware, and inside hardware we have a motor. Okay. In the motor, when you run, let's say whenever you run, let's make a pulse. I mean, suppose we have a hardware like this. The motor is running, and whenever you rotate, okay, whenever the motor rotates, you are making pulse. In that case, you make that kind of pulse and connect to here, then this pin, now we get pulse. Whenever the motor runs, then you get a pulse, right? So this particular pin is to get the external pulse. You can provide whatever pulse you like, okay? And this is the second source. What's the difference between these two? The same thing is that both one is pulse. This one is pulse, this one also is pulse. But difference is that this pulse is from internal clock, because this clock is already there in your board, 12 megahertz. So this is the internal source, whereas this one is from external source, because this pin is open. You can connect whatever you want from the external. Okay, so this is the external source. This is the internal source. Okay, internal source. That's the difference. So from the internal source, we call the timer. External source, we call that as a counter. Why is that? Why do we call this one as a timer? Because this internal clock is fixed. You cannot change this because this is already there in internal. So this is fixed Therefore, we know exactly what's the clock here. In this case, it's 1 megahertz. So since we know the 1 megahertz, if you want to measure a 1 millisecond delay, let's say that's what you want. I want to measure the 1 millisecond delay. In that case, how do you measure 1 millisecond? You are going to count how many clock we have. Let's say we have a 1 megahertz here. 1 megahertz means what? 1 megahertz means you're going to get a pulse in every 1 microsecond. Right? 1 megahertz, right? 1 megahertz you can do inverse of that. 1 megahertz basically means like you have a clock like this, right? Like this. Basically means that the symbol duration or the clock duration, it's like 1 meg, which is 1 microsecond. So this duration is 1 microsecond. You are going to get a pulse every microsecond. You get a pulse. So let's say you want to count 1 millisecond of delay. Then what do you want? How can I do it is that I know that this is fixed. This is fixed to 12 megahertz. Therefore, here is fixed to 1 megahertz. I know that I get a pulse, 1 pulse every microsecond. So what I need to do here is that I need to count 1,000 pulses. Okay, because I have a 1 pulse in every microsecond. So I count 1,000 pulses. That is exactly 1 microsecond. Right? Because I have a pulse in 1 pulse duration is 1 microsecond. So I have 1,000 pulses, then 1,000 pulses is 1 millisecond. Right? 1 microsecond times 1,000, it's going to be 1 millisecond. So that's how you count the certain delay. So in order to use a delay, you want to depend on the internal clock. Because in this external clock, you never know. Sometimes, depending on what you connect, maybe you get a very fast clock or maybe very slow clock. You can connect to whatever you want. So this one, we call it as a counter. But in this case, this is a fixed. So we know that it's 1 microsecond. Pulse is 1 microsecond. So in order to measure a certain delay, you want to use this one as a source. So that's why we call this timer. Now, there's a switch here. Inside the hardware, we have a switch. It can be either this one or this one, depending on which one you want to use. In this example, it goes up here. So I want to use this one. So how to switch? That is based on this bit. Where's this bit? Right here. Counter or timer. It's a selection bit. If you make this bit to 0, that means now I want to use timer. If this particular bit is 1, then I want to use counter. Okay? You are basically selecting the sources. You can use it as timer or you can use it as counter. Okay? So that's this switch, and how to switch based on this bit. Okay? That's what it is. So you use this one as a source. Eventually, each one of these is a pulse. This is a pulse. And what you want to do is that you want to select which source, which pulses you want to use. And I want to count like 1,000 pulses. That kind of counting is done this stage. 2 timer stages. That's next slide. Okay, in the next slide, we're going to count how many pulses we want. Right here, in this picture, basically shows you how to control the pulses. The counting is coming later, next slide. Okay? So again, based on this bit, C/T, you can use this one as a source or this one. Okay? Now let's look at this part. This part. This part is to control. Look at this one. What is this one? This is AND gate, OR gate, NOT gate. Okay, so this is simple logic. So let's think about what it is. Here, this particular pin is controlled by this bit. What is this bit? TR0. That's a run bit. So let's say I want to have this run bit to 1. In that case, you have a 1 here, 1. Okay? When you have a 1, then, okay, this input is 1. In that case, the second input also has to be 1 in order to make output 1. But let's say now, the second input is 0. In that case, this is still 1, but the second input is 0, then you get 0. So when you have a 1 here, then you have a 1 here, 1. 0 here, 0. Okay? So what that means is now this system is on. Now, think about the other way. Let's say I want to make this one as a 0. In that case, it doesn't matter what you have. Okay? If this is a 0, then you always get 0. Okay? It doesn't matter. Maybe this is 1, but still that no problem. Still it's ignored. When you have 0, then it's always 0. So that's a case of off the timer, because you always get 0. In this case, right, what is this switch? This is the switch to connect. This is the first stage. This is the next stage, timer stage. So if this is a 0, that means disconnected. Okay? So no pulse is going there. We have a pulse coming in, so that pulse has to go to the next stage. But if you have a 0, then it's disconnected, so you get nothing. You don't have any pulse. So this has to be 1. That means switch is closed. So now the pulse is going there to the next stage. So this one has to be 1. That is like we make a timer on. Okay? So in order to make this on or 1, this one has to be 1. Okay? That's why we call this particular bit as a run bit. Okay? This should be 1. And in order to make this to be 1, we also need to make this to be 1. 1, 1. That way, this is 1. So let's think about this one now. We want to make this to be 1. In order to do that, this is an OR gate. So in this OR gate, either one can be just 1. In that case, the output is 1. Now let's think about the gate. What is a gate? In the hardware design, maybe some of you are probably taking the courses of VLSI design or some circuit design, right? In some of the design, hardware design, you sometimes see words like a gating, or gating. So what is a gating in hardware design? Gating basically means, what is a gate? Gate is like a door, right? So when you open the door, when you open the gate, then you can come and go. But when I close the gate, no one can come, right? Because the door is closed. Something like this. Gating is to block something or no block. So what that means is if the gating is 0, if a gate bit is 0, that basically means that I don't want to use gating. Meaning that this is always on, always, because I don't want to use a gating. So this is always on. Think about this. This one is 0. Then this is not gate. So therefore, right here you have a 1. Okay. So when you have a 1, what happened? This is always 1 because this is OR gate. So once you have a gate 0, then this is always 1. So this is always on because I'm not using gating. But now think about this one. Now I want to have a gate to be 1. That means now I want to do gating. So sometimes I want to close it or open it. Close, open, close, open. Okay? That's the gating. So I want to do that. In that case, you want to make it 1. If you make this gate bit to be 1, now what happens is this right here is a 0. Okay? Because I have a gate bit to 1. This is not gate. So here is a 0. What we want eventually is 1 here at the output. But we have a 0 here. So therefore, now if this one is 1, we have a 1. If this one is a 0, then we have a 0. So it's like a gating now. Okay, you are enabling gate by setting this 1, and this particular second one is interrupt 1 0. What is that? That's this pin. Based on this pin, now you are gating. If I make this 1, then it's 1. If I have a 0, then it's 0. Okay? So now I'm gating. Sometimes if I want to enable it or disable it, disable it by this pin. Okay? Based on this pin, I want to enable it, disable it. That's called gating. So in order to do gating, I want to have this bit, gate bit to 1. So that's hardware logic. So all these things is to eventually make this 1 or 0. That's what we want. Okay? So simply speaking, this is the clock pulse. Okay, these are clock pulse. You have two different clock sources, internal clock or external clock. Okay? Eventually these are pulses. And each pulse eventually has to go to the next stage. So in order to go to, you select one of these sources, and this pulses now has to go to the next timer stage. But to do that, we have to make the switch to close, right? Because that way the pulse should go. If you make it open, then the pulse is disconnected. You are not going to get anything. So in order to make it close, we have to make this to be 1. To make 1, you need to enable this by setting this bit to 1. And also, sometimes you may want to use gate or no gate, depending on that. If you have a 0 here in the gate, which means that I don't want to use gate, in that case, this one will be always on, always 1. But if you want to use a gate, then you want to make this bit to be 1, and now depending on what you have here, sometimes you want to have on, off. It's like a gating. So gating can be controlled by this logic. Okay? Eventually, this kind of gating will affect this switch. It can be on, off if you do gating. No gating, it's going to be closed all the time. That's how you use these things. Okay? So far, in this register, we are only talking about timer 0. Okay? Timer 1 is the same because you have a same set of registers, right? Same set of bits. In timer 0, so far we looked at this bit, run bit, right here, and gate bit, right here, and counter or timer selection bit, right here. Okay? We haven't talked about overflow bit. Okay, I'm going to talk about in next slide. Okay, so these things, these are the conditions that I just mentioned. So you need to remember how to enable this source, okay, and hardware logic. Now let's go to the next stage. So far we looked at this, right? We are going to the next stage, timer stage. Okay, that timer stage is this one. Now in the previous stage, let's say we close the switch. So now we are getting pulse. So we are getting pulses here, pulse. In the timer stage, we have 4 different choices of timers. Timer 0, 1, 2, 3. We have 4 different timer mode. Since we have 4 different timer modes, you need to select which mode of timer you want to use by setting these 2 bits. We have 2 bits for timer 0 and the other 2 bits for timer 1. And again, let's talk about timer 0 only. We have 2 bits, M0 and M1. You need to set these 2 bits, like this one. If both bits are 0, 0, that means I want to use timer mode 0, this one. And if I set it like 0, 1, like this, then what that means is I want to run this timer to timer mode 1. Okay, like this, right? Depending on how you set these 2 bits, you are going to select only one mode, one timer mode. Okay, so now let's look at the details of what's the difference of each timer mode. First one here, timer mode 0. As you see here, this is a 13-bit timer. Okay, I'll tell you what that means in a minute. But let's look at the difference first. Timer 0 is a 13-bit timer. Timer 1 is a 16-bit timer, bigger timer. Timer mode 2 is an 8-bit timer. It's a smaller timer. But nice thing is that it is auto reload feature. It's an auto reload 8-bit timer. And the last one is actually mode 3 is a little bit different. This one is a 2 different 8-bit timer. So let's look at one by one. So here is all of the timer modes. 13-bit, 16-bit, 8-bit, but auto reload, the split timer. So here's the thing. You see here that you see the TLX, THX. These are registers. Another registers. X means timer number. So X can be 0 or 1. Okay? It can be like TL0, TH0 for timer 0, TL1, TH1 for timer 1. So these are two different registers for timer. Okay? But these two registers are not to control or mode selection. Going back to the previous slide, here we talked about the control register. Okay, this is for control register, and this is for mode selection. Okay, but we also have these registers, right? TH and TL. This is not to control or not to select mode. This is to count. Okay, this is for controlling. This is for mode selection. But this is to count the event. Okay, we need those registers. So we have a L means low, H means high. Okay, low. We have a timer low, timer high, 0, 0. Each one is 8-bit. We have two different 8-bit registers. Here's how things work. Going back to the previous slide. Again, in our example, let's say we have a 1 megahertz clock right here, okay? Which means you get a pulse in every microsecond. 1 microsecond, you have a pulse. Now, let's say we control these things so that we close this switch. So now this pulse, 1 megahertz pulse, 1 megahertz clock is coming all the way to the timer. Now suppose that what we want is to measure the 1 millisecond of delay. Okay, let's say that's what we want. And we know that we are going to get 1 megahertz clock. So what we need to do is to count 1,000 pulses. Each pulse is a microsecond. So when I count 1,000 pulses, that's going to be exactly 1 microsecond. So that's what we want. I want to count 1,000 pulses. If you want to make a 2 millisecond delay, you can count 2,000 clocks. Simply, it's a matter of counting. So to do the counting, here what happened is that, let's say your pulse is coming in, and those pulses now go into here, and this particular register is counting. It's a counter. So whenever you pulse coming in, you basically increment this value. The hardware do that for you. Okay, so you get a pulse. Initially, let's say it's all 0, initialized to 0. Then you get 1 pulse, it becomes 1. Next pulse becomes 2. Next one, 3. So these registers will automatically, hardware will automatically count number of pulses coming in. So what do you need to do? You don't have to do anything. You're just watching this one because hardware will automatically. You're going to get the pulse, right? Pulse is continuously coming in. And once the pulse is coming in, pulse train is coming in, the hardware, timer hardware will keep incrementing. Okay, every time you get a pulse, you just keep incrementing. So what you need to do is just watch this value until this value becomes 1,000. Okay? Maybe that's what you want. But look at this one. You have a pulses in every microsecond. So this value will be incremented very fast. Right? this value will be changed in every microsecond. So how can you catch, you watch this value until this value becomes 1,000, so you never know, right? Because it's so fast. You cannot catch it. So therefore, what you need to do is that you need to set this timer a little bit different way. What is the best way to catch exactly 1,000 pulses? It starts from 0, then it just keeps incrementing. So it's very difficult to catch exactly the time of 1,000, right? Because it changes very fast. You never know, right? So what is the best way? I want to count only the 1,000 exactly. But I cannot watch it because it's incrementing too fast. So I cannot find the moment that timer becomes 1,000. So that's why here's the best way. In this case, right, we have a 13-bit timer, which means that we are going to use 8-bit here and 5-bit here. Okay? Putting together, it's going to be 13-bit. 5-bit here, 8-bit here, make it 13-bit. So now let's say we have a 13-bit timer. This is 13-bit. Okay? We have a 5-bit here, 8-bit here, so it's all 13-bit. What is the maximum value you can have in 13 bits? 8K. Yeah, 8K, right? Because 10 bits is 1K, and we have a 3 bits more. 2 to the 3 is 8, so definitely it's 8K. So using this one, if you start from all 0, then it's just incrementing, and when you have all 1, that's the maximum value. When you have all 1, that's going to be 2 to the 13 minus 1. Right? If you have all 1, that's going to be this value. This is the maximum value you have. And let's say this is the maximum, all 1. And let's say we have one more pulse coming in. In that case, this timer will automatically increment. Right? Let's say this is the maximum we can have. Now we have one more pulse coming in. Then what's going to be the value? It becomes 0. And we have a carry now. Right? When this one to this one, from this one to this one, now we have a carry. So now, easy way to detect exactly 1,000 bits is that we are going to use carry. Because when carry happens, then the carry basically tells us that, okay, now there was overflow. There was a carry. Okay? So we want to use a carry in order to detect, in order to count exactly 1,000. So how can you do it then? This is the event when carry happens. And we want to make carry happens after exactly 1,000 pulses. How can you do it? This is the maximum value we have, right? Yeah, this is the maximum value we have. From this value, let's say I want to count 1,000 pulses. I want to subtract 1,000. Okay? In that case, you get some value, right? You're going to write this value as an initial value into the timer. That's what you want. Actually, not plus 1. Yeah, I think that's right. Yeah. So this is the initial value you want to write into the register. Why is that? Let's say, let's pick a simple example here. Let's say, let's think about the 8-bit timer. Let's make a smaller timer, 8-bit. And I want to, let's say, count 20 pulses. In that case, the maximum value you can have with 8-bit is the 2 to the 8 is a 256. What I like to have is that 256 minus 20 because I want to count only 20 pulses. So what I do it here is that 236. Let's make it 16. Just make it simple. 16. In that case, minus 16. Then we have a 240. So what is a 240? 1, 1, 0, 1, 2, 3, 4, 5. Not this one. 1, 0. That's 240. Okay. So for the initial value in my timer, I'm going to set this value, 240. That's my initial value. Before I run the timer, I set it this way. This is the initial value. When I do it, when I set this one as the initial value, now I want to run the timer. Then in the timer, we have a pulse. We have a one pulse, then you're going to add it. One more pulse, you have added. Okay? So whenever you have a pulses, then the hardware will keep adding like this. And until that you have a 16 pulses coming in, now what happened? This one becomes now all 0 and the carry happens at that time. Because that's how we design it, right? We set the initial value 240. So once you have a 16 pulses coming in, then the value remaining here becomes 250. Let's say we have a 15 pulses coming in, 15. Okay, so far we have 15 pulses. Then the value inside here becomes 255, which is 1, 1, 1, 1, 1, 1, 1, 1. And one more pulse coming in, now this value becomes all 0, and now we have a carry is on. That's how exactly we can count 16 pulses. Because by watching the carry, once the carry flag is on, that's the time that we have a 16 pulses. Same thing here, right? If you want to count 1,000 pulses, then maximum value minus 1,000, this is the initial value you want to program it here and run the timer. Okay? And then every time you have a pulse, this value will be incremented. Okay? And when you have 1,000 pulses coming in, now the remaining value here becomes 0, all 0, and now we have a carry. That's the time that now you have 1,000 pulses. That's exactly time of 1 millisecond of delay. Yes?
But I think there has to be 2 to the 13 minus the top.
2 to the 13 minus?
Because the lowercase you did 256 minus 16, but the uppercase you did just 2 to the 13 and minus the top. The lowercase you didn't. They kind of like 2 to the 8 negative 1, I mean 2 to the 8 minus 1 minus 16.
Oh yeah, right. Yeah, I think you're right. Yeah, right. So this one has to be the value, this one, right? Yeah. So this would be the initial value writing in here, okay? This probably is the initial value you want to write here. That way, when you have 1,000 pulses coming in, then now you have a carry, and all the bits in the remaining in the counter becomes 0. Yeah, right. So this is the initial value you want to write. And if you want to count 2,000 pulses, then simply this is going to be the initial value in your program, in your counter. That's how you run the timer. Simply, okay? Difference between these is that this is a smaller timer. We have a 13-bit. So the maximum pulses you can count is this much. Actually, 2 to the 13. This is the maximum number of pulses you can count with this timer. But this timer is a 16-bit, 8-bit here, 8-bit here. So therefore, with this timer, you can count more pulses, 2 to the 16 pulses. Right? So simply the size is different. Okay? So this is really easy to understand. However, here's one thing. Let's go back to here. Generally, let's say, going back to our example, let's say I want to flash my LED in every millisecond. In that case, you count millisecond delay, right? And then flash it, and again you want to count the delay. So this kind of delay measurement typically is done repeatedly, right? You measured 1 millisecond, and next time you again want to measure the 1 millisecond delay. So this kind of 1 millisecond delay happens generally, right? In that case, what you need to do here is that in order to measure 1 millisecond delay, this is going to be initial value you have, right? So let's write it. Let's write this value here as an initial value and run the timer. Okay, and then you get the 1,000. Let's say this is 1,000. Then you get 1,000 pulses. After 1,000 pulses, that's exactly 1 millisecond. Now we have a carries on, and this value now becomes all 0. And that's exactly when you have a 1 millisecond delay. But that's not the end. We want to measure another millisecond from that time. Okay, we want to keep measuring millisecond. So from here, we want to delay another millisecond. Now what's the problem? This value now becomes 0. Okay? So when is the time that we have another carry on? This time, right? Because this one, at the very initially, we write this value as the initial value. But once the carry is on, the value remaining in this register becomes all 0. So from that time, it takes this much time to become another carry. Do you understand what I'm saying? In that case, it's not 1 millisecond, right? Maybe only the first time it was 1 millisecond, because at that time I programmed this one as initial value. But 1 millisecond of delay, only the first time. On the second time, it's going to be a lot of much more delay, because it starts from all 0, right? And you're going to count these many of 8K of delay. Only then it'll become another carry. So that's wrong, because we want to keep measuring 1 millisecond delay. So how do you need to do? What you need to do in this case is that whenever you have a carry, that means now we have a 1 millisecond of delay. Then we know that the value becomes all 0 now. So what do you need to do? You need to stop the timer and program this value again and run it. So you have to keep writing this value, initial value. Whenever the carry happens, okay, whenever the carry is on, then you need to reinitialize it. Only then it becomes a 1 millisecond delay. Okay, every time you need to initialize it. That's a lot of work, right? Because you have to do initialization every time. So that's a lot of work, but these two timers, you need to do that. Otherwise, you cannot count exact numbers. However, in mode 2 register, that is done automatically by hardware. That's why we call this auto reload. So let's look at here. We have, in this case, it is an 8-bit timer. We only have 8-bit. 13-bit, 16-bit, but in this case only 8-bit. So the number of pulses we can count is only maximum 256. But small timer. But nice thing about this is that whatever value you have in TH0 will be auto reload. Okay, auto reload whenever you happen. Okay, whenever you these carries. Oh, by the way, whenever the carry happens here in the timer, that's the time now you see the timer overflow is on. Yeah, I forgot to say that. So here, right? TF0 means the overflow, timer overflow 0. Go back here. This bit, this bit. So whenever this happens, right? This condition, all 1 and it becomes 0, so therefore now carry flag is on. That's the time now you have this bit is 1. Okay? Whenever the maximum value and it becomes 0, now we have this value on. So what you need to do? What you need to do is that you can watch this value. Watch this bit. And if this bit, time overflow bit is 1, then it's going to be, that time is going to be the 1 millisecond. Okay? You just watch this bit. If this bit, initially it's 0, and if this bit becomes 1, okay, hardware make this 1 whenever that condition happens. This becomes 1, then that's the 1 millisecond. In mode 2, let's think about this way. Coming back to our previous example, let's say this is a TL0, okay? And I want to measure 16 pulses. What's the initial value you want to write? You want to write 240 because I want to count 16 pulses, right? And I want to initialize this register with the 240. Okay, same way. But instead of writing this value here, in mode 2, what I'm doing is that I'm going to write this value, initial value, into here. And then run the timer. Then the hardware, as you see here, hardware will automatically get this value and write it here. So hardware will copy this value here. And then every time you get a pulse, then you increment 241, 242. This one is same, right? You don't change anything here. But this one is basically a counter. So this one keep incrementing like this, same way. And then whenever this counter becomes all 0 and the timer overflow becomes 1, then hardware timer will automatically, when the timer overflow becomes 1, that's the time that the value here becomes 0. Okay, whenever this one becomes 1, this one becomes 0. Then hardware automatically copy this value back here and do it again. So that's why we call this one as auto reload. This is a very nice thing, right? It's auto reload. In this case, it's not. You have to program it every time. Okay, but this one it's done automatically. The last one, it's not popular. We don't use it much. But this one actually is using two different timers. Since we have TL0 8-bit, TH0 8-bit, we have two different 8-bit registers. We are going to separate TL0 and TH0 and make two different timers. This is all about timer 0, hardware timer 0. So inside the one hardware timer, you are actually making two timers. That's what it is. But this is not that popular. I think this one has some problem, like some auto reload. So typically, right, this is again the 8-bit timer. So if you want the 8-bit timer, we typically use this one. And later, probably next week, we're going to learn the serial port. And serial port, you need a timer. And we are going to use this timer. So in 8051, most likely we use this timer because of the auto reload feature. Okay, so we're gonna once you exercise with the serial port, then now you can understand better about this timer mode. So these are examples how to use the each timer mode. But you can take a look at it, each one. Here. In order to use a timer, first thing to do is that you need to set the timer mode register. So in this case, I'm writing the 44H to the timer mode register. What is a 44? 44 is meaning that 0100. So let's go back here, T mode. So this is a T mode. I'm writing 400, which means that 0 here, 1 here, 0, 0. 0, I have a 0 here, meaning I don't want to use gate. So this is always on. Okay, always on. 1 here means that I want to use a timer as the source. Okay, I want to count external pulses. Okay, since I said 1. 0, 0 means that I want to use my timer as timer mode 0. Okay, so those kind of selection is done by this way. 40 means that I want to gate is disabled. I want to use timer 0. I want to use counter, not the timers. And this value, I'm writing 0 to TL0, 0 to TL1. This is a part of the initialization. I'm writing the zeros in both timers, timer values. And actually, not the TL0 and TH0. These two are the timer registers for timer 0. And TL1 and TH1, these two are the timer registers for timer 1. And I'm initializing timer 0 with these two. And I'm initializing timer 1 with these two. And the reason that I'm writing this value is this one. Okay, you can look at this one. What I want to have is that I want to make this timer 0 to be overflow after this much. Okay, that's what I want. The reason that I'm writing, calculating from 256 minus 255 is because of that, right? So, and this one, set B means that set bit, or particular bit I want to set it. And what I want to set? TR0. What is TR0? This particular bit. So when you set this bit, like to be 1, then now you run it. So before you set this, you need to program all the other things. You need to make all these other registers to be prepared. Now then, you just make it 1, then it runs. Okay, that's the procedure. So this is the example, and this is what happened. And whenever your timer pulse is coming in, counter pulse is coming in now, it's keep incremented. And whenever TH0 becomes all 1, and next pulse coming in, then it becomes 0, that's when you have an overflow flag, timer overflow flag. Timer mode 1, it's pretty much the same. The only difference is that this one is a 16-bit register. Timer mode 2, this is important, more important. You can write the program mode, timer mode into different value, like 66. Okay? Again, 66 means that gate is disabled, timer mode 2 and counter. And you can write it this way. Okay, you can write it this way. Remember that I'm not programming TL0 and TL1 because you don't have to write. Why? Because when you run the timer, this value will be automatically copied to a TL0 and TL1. So you don't have to program TL0, TL1. This is the initial value you want to use for the timer. Okay? For my timer 0, I want to count 3 cycles. Therefore, you do 256 minus 3. That's going to be your initial value, right? No, actually, I'm writing. Oh, yeah, that's right. Right. So that's so your initial value is going to be this one because I want to count only 3 cycles. For the timer 2, with the timer 2, let's say I want to count these many clock cycles. So therefore, this is going to be the initial value for the timer 1. So once you set the timer TH0, TH1 this way, and once you correctly set up the mode 2 this way, now you can set B, TR0. Now you run the timer. Then it's automatically reload and it's keep running. And every time this cycle, clock cycle comes in, then now you see the overflow flag 1. TF0. And every time you have this much of cycle coming in, you have TF1 flag. Okay? Yeah. So this one, I think we are not going to cover because this one is not that important. Maybe we have an issue later, then we're going to look at it. Any question? Okay, then see you next week.